Hello everyone. So in this video, I will be going through the review questions, the mole. I will not be going over how to do a molar mass. You should be able to look at the answer key and figure that out. But I am going to be going through mole conversions, empirical formula, other things that maybe require a bit of an explanation. All right, so 1, 2, and 3, they're just straight mole conversions. You should think through the process. For example, how many times is mole mentioned? How many conversions do you need? What keywords are given? And then set up your problems. So for the first problem, where it says how many molecules are in 6.25 moles of SF6? Mole is mentioned once, so there's one conversion. The keyword is molecule. So therefore, we are going to need to use Avogadro's number. We're going to set up our train tracks. So we're going to do 6.25 moles, put it over 1. The unit mole comes down, molecule goes to the top. Remember, do units first. 99% of the time, 1 is going to go next to mole. We already determined we needed Avogadro's number. 6.02 times 10 to the 23. Units for mole cancel, multiply it out, and we get 3.76 times 10 to the 24 molecules. Now remember, we don't care that we're dealing with SF6. This conversion does not care about the identity of the substance. Question 2 says, how many grams are in 4.22 moles of ammonium nitrate? So mole is mentioned once. We have one conversion. Key word there is grams. That means we need to use a molar mass. And we're going to need to use a molar mass of the NH4NO3, which we did calculate in number 6 up above. So one conversion with a molar mass. So 4.22 moles. Put it over 1. Mole comes down. Gram goes to the top. 1 goes next to mole. The molar mass we calculated for NH4NO3 was 80.06. Mole cancels. Multiply it out, and we get 338 grams. Last question, or number 3. We have a certain mass of FeCl3 is how many moles? Mole is mentioned once, one conversion. Keyword is grams, therefore I need a molar mass of FeCl3. I calculated that mass in number 8 up above. So now I start with 250.76, but now it's grams. Gram comes down, mole goes to the top. 1 goes next to mole, and the molar mass was 162.20. Unit for grams cancels. So I divide the mass by the molar mass, and I get 1.5460 moles. Okay, so question 4, we're dealing with caffeine, which is C8H10N4O2. And first question is we want to know how many moles there are. So if we have a certain amount of molecules, and I want to go to moles, mole is mentioned once, one conversion. So it's going to be 1.84 times 10 to the 24 molecules. Put it over 1. Molecule comes down. Mole goes to the top. 1 goes next to mole, and then we put Avogadro's number on the bottom. This is a problem where if you don't know how to use your calculator, you're going to get something times 10 to the 47. Okay, so make sure you know how to use your calculator. We're going to get 3.05 moles. B says how many grams? Well, we have this many molecules. Now I want to go to gram. Mole is not mentioned, so it's going to be 2 conversions. Molecule means we need to use Avogadro's number. Grams means we need to use molar mass, and it's going to be the molar mass of the caffeine. That molar mass is 194.22. I do not care about molar volume here because I'm not dealing with a gas and it's not asking for a volume. So we're going to set this up, and we're going to start with 1.84 times 10 to the 24 molecules. put it over 1. Molecules comes down. Mole goes to the top. 6.02 times 10 to the 23rd goes next to molecule. Now mole comes down. Gram goes to the top, and now I can use the molar mass. So 1 mole is 194.22 grams. And I do the math, and I get 594 grams. Now, C is how many grams of nitrogen in this many number of molecules. There's a lot of different ways we can do this, and I've been trying to stress this in class, that there are different ways we can do it, and we're going to do this using mole conversions rather than a percent composition. So remember, the subscripts here, the 8, the 10, the 4, the 2, they have to do with a ratio of part to the whole. It means that I have 8 atoms of carbon per 1 molecule of caffeine, 10 atoms of hydrogen per 1 molecule of caffeine, etc. It also means I have 8 moles of carbon per 1 mole of caffeine, 10 moles of hydrogen per 1 mole of caffeine, etc. That gives us a conversion factor to go from the whole to the part. I'm going to start with the 1.84 times 10 to the 24 molecules. The good habit to get into is, if you're not in moles, get to moles, because once you're in moles, you can get to any other unit you want to. So our molecule is going to come down, mole goes to the top. But I'm now going to put moles of caffeine here. I'm going to put a little additional label. 1 mole of caffeine has 6.02 times 10 to the 23 molecules. Now that I'm at moles of caffeine, I can switch from moles of caffeine to moles of nitrogen, because I know there are 4 nitrogens per every 1 caffeine. So 1 mole of caffeine contains 4 moles of nitrogen. This now has allowed me to switch to talking about just the nitrogen. Now that I'm at nitrogen, I can now switch from talking about moles of nitrogen to grams of nitrogen using the molar mass of nitrogen. So molecules cancels, moles of caffeine cancel, moles of nitrogen cancel, and I am left with grams, and I get 171 grams of nitrogen. Number 5 is exactly like the last one we just did with caffeine. If I have a certain mass of C12H26, how many moles of carbon atoms? Okay. Well, if you are not in moles, get to moles. So how do I get from grams of C12H26 to moles? I need a molar mass. And the molar mass of that is 170.38 grams. So I'm going to now start with 52.89 grams of C12H26. Put it over 1. Gram comes down, mole goes to the top. 1 mole has a mass of 170.38. Now that I'm in moles, I can go anywhere I want. And I can go from moles of C12H26 to moles of carbon, because I know I have 12 moles of carbon per every 1 mole of C12H26. So moles of C12H26 to moles of carbon, I have 12 carbons per 1 C12. My units cancel. I complete the math, and I get 3.73 moles of carbon. Number 6, we're going from molecules to mass. Mole isn't mentioned, so therefore I need 2 conversions. Molecules means I use Avogadro's number. Mass means I use a molar mass. So I start with 2.93 times 10 to the 24 molecules. Put it over 1. Molecules comes down. Mole goes to the top. There are 6.02 times 10 to the 23 molecules in 1 mole. And now I can go from moles to grams. 1 goes next to mole. And we calculated the molar mass of SF6 in number 2 up above, and that is 146.07. And I get an answer of 711 grams. Okay, percent composition. So in order to do a percent composition, you're to do the mass of the individual element divided by the total mass multiplied times 100. So sucrose, there are 3 elements. We need 3% compositions. So the percent carbon is going to be 12 times 12.01 because that's the mass of your carbon from the periodic table. The molar mass of C12H22O11 is 342.34 multiplied times 100, and I get 42.10%. For my percent hydrogen, I have 22 hydrogens. Mass of hydrogen is 1.01. Molar mass of the whole thing is 342.34 multiplied by 100, and I get 6.49%. And my percent oxygen is going to be 11 times the mass of oxygen on the periodic table over 342.34 times 100, and I get 51.41%. So that's all you have to do. Check to make sure it adds up to 100, and then you are good to go. All right, question 2. There are 2 elements. So you need to do the percent composition for iron and for oxygen. So for percent iron, it's going to be 3 times the mass of iron, which is 55.85, divided by the total mass, which is 231.55, multiplied by 100, and you get 72.36%. My percent oxygen is going to be 4 times the mass of oxygen, divided by the total, which is 231.55, times 100, and I get 27.64. Check to make sure they add up to 100. You're good to go. I'm not going to do out number 3, but you do need percentages for carbon, hydrogen, nitrogen, and oxygen. You can look at the answer key for that. All right, this question is very similar to the questions above, where we're trying to get from the whole to the part. Now, when it says how many grams of iron can be obtained from this amount of magnetite, well, we learned from above that magnetite is Fe3O4, and that 72.36% of that is iron, which means in any sample, about 72% is iron. So all I have to do is multiply 155.4 grams of the magnetite times 72.36%. And I get 112.4 grams. Number 6 is exactly the same, except now we're dealing with sucrose. And we learned from up above that sucrose, flip my paper, is C12H22O11. And we learned that the percent of oxygen in sucrose was 51.41%. So all I have to do is take the 250 grams, multiply by 51.41%, and I get 128.5 grams of oxygen. All right, here we're trying to get an empirical formula for MSG. Now, whenever you're doing empirical formula, I recommend you just memorize the little poem so that you know those main steps that you need to take. So percent to mass to moles, divide by smallest, multiply till whole. Now here we have a percent. So what we're going to do is we're going to change the percent values to grams. So carbon is 35.5 grams. Hydrogen is 4.77 grams. Nitrogen is 8.29 grams. Sodium is 13.6 grams, and oxygen is 37.9 grams. Done. Percent to mass. Now we do mass to moles. So we're going to take each and divide by molar mass. So 1 mole, 12.01 grams. I get that from the periodic table. 2.956 moles carbon. 1 mole, 1.01 grams. 4.2723 moles. Nitrogen, 1 mole, 14.01 grams. And I get 0.5917. Sodium, this one, there's a bunch that we have to do. It does get a little tedious. And I'm getting all of these numbers, the 12.01, 1.01, those are from the periodic table. So 0.5916. And then oxygen, 1 mole is 16, 2.369. So we've done percent to mass, mass to moles. Now we divide by smallest, and the smallest is 0.5916. So we divide all of them so that we can get a ratio. So divide them all. And if I get a whole number for each of these, I'm done. So I get 5.8114. Now you can only round if you're at like 3.999 or 3.90, then you can round, or 4.1, then you can round. But if you're at like 3.8 or 3.7, you cannot round those ratios. Then you would have to multiply till whole. Now these become my subscripts. So it's C5, H8, N, Na, O. And remember, be careful with your capital letters. Do not write completely capital letters. Make sure you have the lowercase letters where needed. Okay, in this problem, we're not giving percentages. Instead, we are given just masses. In that case, you use the masses as given. So what we're going to do is we have nickel, we have carbon, we have nitrogen. So I have 10.52 grams of nickel, 4.32 or 38 grams of carbon, and 5.10 grams of nitrogen. Then I need to convert to moles. That's the second step. So 1 mole, nickel is 58.69. I get that from the periodic table. And I get 0.1792 moles. Carbon, 1 mole is 12.01 grams. And I get 0.3647 moles. Nitrogen, 1 mole, 14.01 grams. And I get 0.3640. Now I divide by smallest. So 0.3640. And I get the following, 0.511. Now I cannot round 0.5 to 1. Instead, I have to multiply by a factor to get to a whole number, and that factor is going to be 2. So I'm going to have Ni, C2, N2. And that becomes my empirical formula. Okay, so this one is an empirical formula with a molecular formula. So we have glycerol. It contains carbon, hydrogen, oxygen. It says the molar mass is 92.11. This is the molar mass of my molecular. I'm going to take that 92.11, put it on top, because remember we have to get the factor, how many empiricals are there, and I'm just going to take that and put it aside. I need to figure out the number that's going to go right there. I need to figure out what is the molar mass of the empirical. In order to do that, I need to calculate my empirical. So I have to go through the whole process, percent to mass, so 39.12 grams, 8.75 grams, 52.12 grams, convert that to moles, and I get 3.257. Hydrogen, convert to moles, 8.663. Convert my oxygen to moles, and I get 3.258. Divide by smallest, and I am going to get 1, 2.66, and 1. Now, generally, I am not going to give you one that you have to multiply by 3. You can't round 2.66. You're going to have to multiply all of those times 3. So it's going to be C3H8O3. That is my empirical. But I need to figure out how many empiricals are in my molecular. Now I need to do the second step. I need to get the molar mass of this. And the molar mass of this is 92.11. Well, that number goes right up there. And it turns out that my factor is just 1. You can have an empirical that's a molecular, or vice versa. I only just have one repeating unit. So my empirical is also my molecular formula. Okay, this question is another molecular formula where I have to get the empirical formula first. So it's telling us that ibuprofen has a molar mass of 206 grams per mole, which means that is the number I'm going to use at the end to figure out my factor. Okay, now the first thing I'm going to have to do is determine my empirical. So I have carbon, hydrogen, oxygen. So I have 75.7 grams, 8.80, and 15.5. So percent to mass, done. Now, mass to moles. 1 mole, 12.01, and I get 6.303. Hydrogen has a mass of 1.01, and I get 8.713. Oxygen has a mass of 16, and I get 0.9688. Now I divide by the smallest. And I get 1, 9, and 6.5. Now I can't have fraction in a fractional ratio, so I have to multiply all of this times 2. So what I get for my empirical is C13, H18, O2. That's my empirical formula. Now I need to get the molar mass of this, and the molar mass of this is 206.31. I have to take that molar mass and put it over here, because this is going to tell me how many empiricals there are in my molecular. Now, this one, I also only have one empirical in my molecular. But if I got 2 or if I got 3, I would need to multiply that times every subscript here. So if I got a factor of 2, I would have to multiply the 13, the 18, and the 2 by 2 to get the molecular. But I only have 1, so therefore this is also my molecular, and that is my answer. We did an example like this in class, but this one is a little different because this one is M2O. The example we did in class was MO. So we have this compound. It contains 16.99% oxygen by mass. We want to know basically what is the unknown metal and what is the molar mass of the compound. Well, I know that the percent oxygen in this is going to be 1 times the mass of oxygen divided by the total molar mass. And the problem tells me that this is 16.99% oxygen. So now what I can do is I can solve for my molar mass. And I did forget one thing, that I have to multiply my percent, my fraction times 100. So now I'm going to use my algebra. I'm going to solve for the molar mass. And I get a molar mass of 94.17. But that is the molar mass of M2O. If I want to figure out what M is, I now need to, 94.17, I need to set this up because it's 2 times the mass of M plus 1 times the mass of oxygen. So now I subtract 16 from both sides, divide by 2. The mass of M is 39.09. And when I look on my periodic table, I see that this is potassium. This is a great example because it talks about a lot of the concepts that we've learned about. So it's a combustion analysis problem that's kind of splitting things up into steps. So we have DDT, which is an insecticide, and it kills insects, particularly mosquitoes. And it undergoes combustion analysis, and we get a certain amount of CO2, a certain amount of H2O, and it tells us that 50% by mass is chlorine. So for A, when it says, what is the number of moles of carbon? What I need to do is I look at this part here, and it tells us that 8.692 grams of CO2 are produced. So we have to get the amount of carbon from that. So I have 8.692 grams of CO2. Basically, I'm going to do a percent composition. I'm going to multiply by the mass fraction. So it's 12.01 grams of carbon per 44.01 grams of CO2. And the grams CO2 cancel. Then I'm going to multiply, because it's asking for moles. I'm going to multiply times 1 mole, 12.01 grams. And I get 0.1975 moles. And that's moles of carbon. Now the next question is saying, what is the number of moles of hydrogen? Well, it tells us here that 0.06339 moles of water are produced. Well, I know that there are 2 moles of hydrogen for every 1 mole of water, so I can do a conversion. I have 0.0639 moles of water. For every 1 mole of water, I get 2 moles of hydrogen. And that comes from the subscript here, 2 hydrogen per every 1 water. So I get 0.1268 moles of hydrogen. Then it says how many moles of chlorine are there. Well, it tells us in the problem that the same mass, 5 grams of the sample, has 50% chlorine in it. So if I have 5 grams of the sample, I multiply that times 50%, I get 2.5 grams of chlorine. Now all I have to do is multiply times 1 mole over the molar mass, and I get 0.07052 moles of chlorine. Now the last question says, what is the empirical formula? Well, I need to take all of my moles, because this tells me the moles of each, divide by the smallest. So just for sake of space, I'm going to divide by 0.07052. 0.7052. Oops, 2. And I get a ratio of, if we have carbon, hydrogen, and chlorine, 2.8, 1.8, and 1. I cannot round those. So the multiple here is 5. Now, on your next assessment, I will not give you one where you have to multiply times 5. If you get one that you have to multiply by, it'll be by 2. So we get 14, 9, and 5, and those become our subscripts. So it's C14, H9, O5. Okay, 7 and 8 have to do with molarity. in calculating molarity. So remember, molarity is the formula, moles of solute per liter of solution. So basically you find the solute, you find the solution, put them in the appropriate units, and plug into the molarity formula. So number 7, we have 0.289 moles of FeCl3. That should be a subscript 3. It should be down here. Dissolved in 120 milliliters of solution. Well, I'm already in moles. This FeCl3 is the solute. I'm already in moles, so 0.289 moles of FeCl3. And 120 milliliters of solution, I put that into liters, 0.120 liter, and I get 2.41, and the unit is a capital M. 8, what is the molarity of 650 milliliters of solution containing 63 grams of NaCl? The 650 milliliters, that's our volume that's going to go on the bottom. I have to convert 63 grams of NaCl to moles. So 1 mole of NaCl has a molar mass of 58.44 grams. And I get 1.08 moles. Now I can plug this into my molarity formula, 1.08 moles. And to convert milliliters to liters, I need to divide by 1,000 or move the decimal 3 places. So 0.650 liters. And I get a molarity of 1.7. Question 9 is something that I need to do all the time if I need to make a particular solution from a solid. So how many grams of calcium hydroxide are needed to produce a solution of 1.66 molar and a volume of 500 milliliters? Well, I know my molarity, that's 1.66. I don't know my moles, but I do know my volume, put that into liters by dividing by 1,000. So now I can determine my moles of calcium hydroxide, and I get 0.83 moles. Now I just need to convert that to grams. So mole comes down, gram goes to the top. Molar mass of calcium hydroxide is 74.10. So I need 61.5 grams of calcium hydroxide. And we're going to say 3 significant figures. We're going to say that there should be a decimal there. Okay, 10. 10 is the one that kids oftentimes forget about a formula, and they tend to get it wrong. Anytime you're given 2 molarities and 1 volume, or 2 volumes and 1 molarity, it's going to be M1V1 equals M2V2. Super easy formula, but kids forget to use it. So you're taking what's called a stock solution, which is a concentrated solution, and diluting it down. So number 10, to what volume should 25 mils of a 15 molar HNO3 be diluted to prepare a 3.5 molar solution? I have 2 molarities and 1 volume. And remember, you can leave the volumes in milliliters because the conversion factor will cancel out. So I have 15 molar, and I have 25 milliliters. I want a 3.5 molar, and I want to know the final volume. Now it's just algebra. So solve, and you get 107 milliliters is what your final volume will be.